So what we have here is a Python encoding of the breadth-first search algorithm we've been talking about for finding shortest paths in these kinds of graphs. In this particular case, there's some infrastructure in the beginning for reading the data for the comic book characters from a file. The one that we're using here is tens of thousands of lines long. So it would be very awkward to put it directly into Python, but pretty simple code for just going through, reading it, and then making links into a graph G. That graph is stored as Marvel G. That's the graph of the comic book characters and the comic books. Then we've got a subroutine called path G v1 v2. And what that does is it takes a graph G, a start node, say a character in the comic book, and an ending node, another character in the comic book, and it tries to find the shortest path between them. In fact, it will, unless there isn't one. So in this particular case, the code here is only going to tell us the length of the shortest path. It turns out that's a pretty straightforward thing to do, but it's not that hard to augment this to actually produce the path itself. But let's just start off with the length. So we create a data structure, distance from start, which is going to map the nodes of the graph to how far away they are from V1. We have an open list, just like we've been talking about, and it's initialized to just the very first node. And the distance from start from that node is 0 because it is the node itself. Now we're going to proceed by checking to see whether the open list is empty. If it's not, then we go into our loop here that says first we're going to pull off the very beginning element of the open list and call that current. And then we're going to delete the very first element of the open list so that it's gone. We're going to talk a little bit later about how to try to make this operation as efficient as possible. But for now, this is okay. It's going to be fast enough. So it takes that off of the open list. And now what are we supposed to do? We loop through all the neighbors. So here we have a statement that says for each neighbor in the list of neighbors of current, what is it going to do? It's going to check to see whether or not that neighbor's been assigned a distance so far. If it has not been assigned a distance, it's because it's not been visited. It's not been marked. And if that's the case, then what we're going to do is we're going to calculate the distance from the start for that node. Well, what is it going to be? The neighbor, the new node that we just discovered, is just one step farther from the start than the node that we're expanding. So we take the distance from the start to where we are now, add 1 to it, and that's the start to this neighbor that we're considering. So this is really the key step that is finding the distance of the shortest path. Once that distance has been assigned, we check, hey, was that neighbor the one we were actually searching for? If it is, we can just be done. We can just return that distance for that node. Otherwise, we have to proceed, and we take that neighbor and we just stick it on the end of our open list so that we'll catch up with it later. And then we're back into the loop, and it's just going to continue pulling things off the open list, assigning them distances until finally we discover the node that we're looking for. Or if the open list eventually goes completely empty, all this falls all the way through, the while loop is done, and it returns false. So instead of actually returning a distance, it's going to return false, meaning I wasn't able to find a path. This could also be infinity, which indicates that there is no bound on the length of the shortest path. It's infinitely large. In this particular case, I'm running it with finding the path from a comic book character called A to one called ZZZax. I figured that was pretty comprehensive if we go from A to ZZZax. And it's a 3 or 4 step chain that you get when you do this with the data that we've got. All right, so let's go through the changes we need to make to actually return the path instead of the distance. What I'm going to do is actually co-opt this variable distance from start. It's not going to be a distance anymore. It's actually going to be the path. So instead of it starting at 0, it starts as just a list consisting of v1 by itself. And the only other change that we need to do is when we extend it, because we've discovered a path from the beginning through current, now it goes to neighbor, all we need to do is that says this now being a list, when we add another list to it, it actually is just appending to the end of it, which is what we want in this case. It might not be the most efficient way to do it, but the things don't get very large, and it actually works pretty well.